Helmholtz equation. First, we need to know who invented the Helmholtz equation. So I'm going to talk about the biography of the inventor of the Helmholtz equation. Okay, Helmholtz equation. His name is Hermann Ludwig Ferdinand von Helmholtz. Okay, this is his picture, and he was born in 13 August 1821 at Potsdam, Prussia. Okay, but he died in 8 September 1894 in Charlottenburg, Germany. Okay, he was one of the most famous German scientists in the world. He has won award of Medici medals in 1868, Copley medals in 1873, Faraday Lectureship Prize in 1881. And as you want to know, the Helmholtz theorem contains three main things. First theorem tells about the function with zero divergence and curl. Second theorem is about vector, about curl and divergence. And third theorem is the circulation of vector tubes remains constant in time. So for the first theorem, I'll pass to my friend.
Suppose we have a vector function of position f, then we state without proof that quite generally vector f can be written as a gradient plus a curl. In example, vector f equal to negative del u plus del cross w, where u is a scalar function and vector w is a vector function, and the minus sign in front of del u is a convention. Now, this decomposition into a gradient and a curl is not necessarily unique. For example, suppose that vector f is a constant. Example, f equal to k vector z. Then, in first equation can be satisfied in many ways. Two simple choices are u equal to negative z k, where vector w equal to 0, and second, u equal to 0 and vector w is at k y vector y. Okay, note that in this example, del dot f and del cross f are both 0. This vector function f is just a constant, but one can could less trivial example of function with zero divergence and curl. Example, vector f equal to yz vector s plus zx vector y plus xy vector z. Okay, note, however, that all these functions do not vanish off infinity. A very important theorem will derive in theorem 2. State that the only vector function with zero divergence and curl which vanish at infinity is 0. In this general form, equation first will not be used in the course and is given for completeness. A much more useful related theorem for function vector f which vanish at infinity and which will satisfy some other condition will be given in the next theorem. Thank you.
Okay, next I am going to explain about the second theorem of Helmholtz theorem. So, suppose that we do not know a vector function f, but we do know its divergence and the curl, where the divergence is a scalar and the curl is a vector functions. And since the divergence of a curl is always 0, so hence for the third equation, it must be divergenceless, where the c is 0. Okay, so now we would like to know if the equations, these two equations, provide enough information to determine f uniquely. Next. Okay, so Helmholtz theorem said that yes, we can find enough information provided that the divergence, the D, R, and the C are vanished fast enough as R is approaching infinity, and it turns out faster than 1 over R squared. And we are interested in the solution for F, which vanishes as R approaching infinity. So Helmholtz theorem also tells us how to calculate F in terms of D and C, and the result are these three equations where F is equals to negative del U plus del W, and this is the equation for U and W. The vector U is equals to 1 over 4 pi integrals of dr prime over modulus of r minus r prime times d tau prime, and for W is equals to 1 over 4 pi integral c r prime over the modulus of r minus r prime times with the d tau. Okay, to conclude, the theorem 2 states that if the divergence and the curl D and C of a vector function f is specified, and if they go both to the 0 faster than 1 over r squared, and if the function itself tends to be 0 as r is approaching infinity, then the function is uniquely given by this equation, and the scalar potential is given by this, and the vector potential is given by this. So the potentials themselves are unique if they vanish as r is approaching infinity, and the W, vector W is in gauge where del vector W is equals to 0. Thank you.
Okay, now we show you the example of second theorem of Helmholtz theory. The first one is the example in electrostatic. We have del dot product with E, we got rho over E naught, and del cross product with E, we get 0. When E is the electric field and P is the charge density, hence we got E equal to negative del V, where the scalar potential V is given by familiar expression, which is this expression. And this expression we'll discuss further in the course. Okay, second example is the example in magnetostatic. We have del dot product with B equal to 0 and del cross product B equal to mu naught J, where B is the magnetic field and J is the current density. Hence, B equal to del cross product with A, where the vector potential A is given in the gauge with del dot product A equal to 0 by this expression. And this expression will also be discussed further in the course. So that's all the example for this theorem. Thank you.
So I'm going to present about the third theorem. So the third theorem basically states that the circulation of a vortex tube remains constant in time. So using Helmholtz second theorem and Kelvin circulation theorem, the above statement can be interpreted as a closed line generating the vortex. The vortex tube is a material line whose circulation remains constant. So Helmholtz second and third theorem hold only for inviscid and barostratific fluid. A barostratific or incompressible inviscid fluid that is initially irrotational will remain irrotational. Hence, such a fluid does not and cannot create vorticity except across curved shock. The proof of Helmholtz third theorem is straightforward. According to Kelvin's circulating theorem, a barostratific or incompressible inviscid fluid has di over dt equal to 0 in everywhere. using this formula, since this has to hold for any s, we have that this formula, hence vector W is equal to 0. Initially, the velocity remains 0 forever. Okay, so we move to the application of Helmholtz theorem. First, as you can see in theorem 3, Helmholtz is used to find the electrostatic with E equal to negative delta V, and in magnetism. So we can Helmholtz theorem also conclude the Lorentz on Coulomb gauge because the field gives rises to integral Helmholtz theorem. Helmholtz theorem also provides significant result pertaining to the meaning of the inverse square radial field, which examples are Newtonian gravitational and Coulomb electrostatic. Okay, last but not least, Helmholtz theorem are important as it is same as Maxwell equation for electric and electricity. Okay, I think that's all from us. Thank you.